Okay, hey everybody. I'm Ryan O'Hara. I'm our technical director of aerospace defense here at nTopology, and I'm just going to talk to you today about how we can perform analysis of lightweight structures. Um, just some quick background before joining nTopology. I was a developmental engineer in the Air Force and have been working at nTopology for the past year, and I'm focused on our aerospace and defense applications. So with that said, just wanted to do a quick intro and talk about how nTopology can really help out in terms of lightweighting. And we can do that in a number of different ways. We can use that doing topology optimization, right? We can do that by periodic infills, where we can put infills in associated with like gyroid structures or lattices, what we're really good at. We can also do things like variable shelling and incorporating that with topology optimization. And then the key here is that we can use like all of these different techniques to structurally lightweight whatever part you're designing, right? And so one of the things though, when we think about these periodic infills specifically is what we're going to focus on today. Sometimes these infills or these architected materials can be difficult to simulate. So nTopology makes it really easy to draw and incorporate these into your design. And we also help out with the ability to analyze these structures and predict them in different ways. And so this is an application where, and for a CubeSat, you basically apply these infills and you create this really stiff, almost like a honeycomb composite structure. And that allows your product to be lighter weight, and then also helps with resonance and a whole bunch of other things associated with reducing mass and increasing stiffness. So I'll get out of the slides. And what I wanted to do is kind of introduce two different techniques here. And what we're going to do is we're going to talk about how in nTopology, you can actually use this workflow that's related to homogenizing an implicit unit cell. And so all that means is that we're going to take a lattice, part of a periodic structure that we showed in the previous product or previous slides, and we're going to talk about how we can use, do some analysis and create this architected material and apply that to an analysis. You can imagine if you had, it's one thing to model an individual unit cell, but it's another thing to model hundreds, thousands, or even millions of these unit cells of a lattice. And so one way that we can do that is we can actually use a workflow or FEA of a single lattice, take the material properties associated with that, and then apply those in a downstream simulation. So what I want to show here is this is a workflow where we define a unit cell and type. We apply material properties to it here on the left, and we define some key features. And so for analysis. And the key here is that if we just show this mesh, we can show basically this is what the unit cell lattice looks like. And when we mesh this part, we can actually use high order elements to do that. So the quadratic elements for FEA analysis. And I do apologize, this will be a little bit finite element analysis heavy when we talk about simulation. If you have any questions, I'd be happy to follow up with you. But the key is that we basically generate an FEA analysis. We apply some loads to this, and we implement this homogenization analysis. And we can see that here. And in doing so, we basically get a material property. And in this case, it's a compliance matrix associated with a part here. And if we all remember good old Hooke's law, basically we end up with a matrix very similar to this when we can get the properties of that. And so we can use these properties as a material block in our solution. And you can see fundamentally, if you haven't seen this before, nTopology enables what we call compound blocks. And so we have a series of inputs. We have a body where we do some actions, and then we have this output, and this output is going to be our material properties. And the cool part about this is when we look at the unit cells over here, let's see, just want to make sure. Yep, we're sharing my screen. I just wanted to make sure that, or when we're analyzing this here, we can look at the directional material properties of this part. And so I'm just going to isolate that. And what you can see here is that based on this unit cell, that we kind of we have directional properties associated with the lattice. And all of these lattices, if they're biased vertically or horizontally, will have different properties associated with them. In this case, we're looking at the equivalent Young's modulus based on direction. And so we'll talk about how we can use that later. In addition to our lattices, we also have unit cells associated with TPMS structures. And if I turn this guy off and we look at our FE model. So we can also take a unit cell like this guy, this TPMS or gyroid, and we can also compute the equivalent homogeneous material associated with this unit cell. And you can see down here in the lower left, we can actually export this as a text file. If we look at that text file and we saw the compliance matrix of the Hooks material, we can see we have this both for the lattice and for the TPMS itself, right? So these are available. A lot of university researchers or others focused on doing analysis of the periodic structures are interested in this kind of thing. And so what I wanted to show now is how we can actually use this. And so this is a top-op bracket that we've used in the past. And you can see this guy here. And the idea is with this, what we want to do is we want to perform some operations. In this case, in the previous use cases, we've looked at taking this center section and optimizing that to reduce weight, right? Because we're carrying loads and different scenarios, but we don't need all this material or all this webbing. And so in the past, we've just looked at a top-op. Actually, let's do this guy here. And when we look at this top-op, you're going to see how we basically removed material from the center section, right? And so what we want to do there, or actually, if we go back to our slides, we've provided a number of different infills here, and so we're just going to recreate some of those here in this scenario. So let's go back. And so what we're going to do to set this up, we had to do something just slightly different in that we know we have an area that we want to analyze. In this case, we're going to treat this webbing, even though we want this to have a lattice like this guy, we don't necessarily want to do all the simulation on each individual lattice. This could be a huge matrix and could be very, very difficult to solve, especially when you're doing design exploration. So an easier way to do that is to actually set up a new model. In this scenario, we're actually going to take this lattice and we're going to break this into components. We're going to create several different ones. In this case, we have a frame that's the outside of this part. We have the inner an inner mount here that we need to tie in as well. And then we have basically the inner volume that we're going to associate with some sort of periodic infill. It could be a TPMS, it could be a BCC or lattice, it could be a variety of different things. But the idea is that we then use tie constraints to tie each of these different meshes together. And then once we do that, and then what we can do here is that we can actually include an analysis of the part here where we include a material property. And this material property is actually going to be from our homogenization. Right? It looks like I may have mislabeled something here. So you'll have to forgive me. Well, this would be a great opportunity for us to look at this. So what we're going to do here is we're going to first look at how I imported the workflow that you saw previously, this TPMS workflow right here. And so all I'm going to do is I'm going to go to my file. I'm going to go File, Import, and I'm going to pick this homogenized TPMS unit lattice. And I would open it here. And then basically I would, I've already imported it in, so I'm not going to redo that, but you would open it here. And then basically you would be able to access the unit cell imports over here via this typing window. And so once we've done that in, I know already that I want to fill this with a gyroid of 10 millimeters on each side for the width, length, and height, and then an approximate thickness of that to be 1 millimeter. And you can actually see this guy if we isolate it here. So we've actually brought in the simulation of this part, right? And it's available. And just like we saw before, we have the directional homogenization available. But now we can actually use this as a material property for our part. And in this case, I would simply drag this guy into the material, and then it's going to show up and be available as an attribute of this inner volume. So now what I've done effectively by doing this is I've filled this entire inner mesh, and I've assigned material properties associated with this homogenization. And so when we do that, we can actually perform our analysis. It's really simple analysis after that, where we just simply, we can look at displacement, and we can look and see how this performs. In this case, we're getting a displacement. It looks about like 1.5 millimeters. And if I exaggerate that with the scale factor, you can see how this part moves up. Obviously, it's not doing that in real life, but you can see how that would be the case. One thing I did want to point out with this lattice cell, especially when we're trying to figure out which type of unit cell to use, if we look at the Young's modulus here, in this scenario, we have about a Young's modulus of 8.5 gigapascals, right? And so if we compare that to, say, a BCC lattice, right, we'll see we'll see the same scenario. In this case, if we look at the directional modulus, in this case, we only get 2.94. So let's just say 3. So in this scenario, the TPMS structure is actually almost 4 times, well, let's just say 2.5 to 3 times stiffer than this BCC lattice. And so in theory, if I did this correctly, we may end up having to rerun this. I'm going to put this BCC in here, and we'll just let this resolve. And what we'll see is that the FEA analysis will show that there's actually a lot more displacement. Previously, we had about 1.5 millimeters. And for the lattice, we'll see something closer on the order of 4 to 5 millimeters once that's complete and running. But we'll come back to that in a second. Ultimately, though, the key is that this is going to solve and run much faster than if we were to actually analyze the individual lattices themselves. So just kind of an interesting way how nTopology is actually able to make analyzing these structures quite a bit easier. With that said, I'm going to let this analysis finish and take the opportunity to open this up for questions. Let's see. Yeah, so a question was, can we demonstrate or break down how you generated the density calculation in your material property analysis? Yeah, so if I go back to this guy here, let that solve. Actually, before we go back to that, I did want to show, so this is the analysis now with the lattice on here, and you can see our displacement is quite a bit higher, 4.72 millimeters versus our original at 1.5, right? And so quite a big difference there in terms of displacement. So, okay. So I will answer Lynn's question now on density calculations. So, and maybe Lynn, while you're there, just wanted to make sure that this is density related to the material itself. You can actually compute the relative density, which is very important when we consider lattices, but that is a separate piece from this. So in this scenario, inputs to this are just these unit cell width, length, and height, and then the unit type. So we could actually, so let's maybe just, while we're doing this, we can just change this. So oftentimes you may want to change or put bias into your structure. So in this case, we're actually going to make this unit cell taller, and by increasing that, and you can see how that will affect your equivalent material properties or your directional material properties. It's just going to take a second to run here in the background. But as we're doing that, you can see how we've defined all these inputs, and all these inputs are just from the blocks associated with the lattice. So you can see these variable chips that are showing up, and we implement those by just right-clicking and selecting them and saying make variable. In this case, I've already made a variable, so it's grayed out, but that is available. The other key here is that we are providing just density as a material property into the FEA analysis of the lattice itself. So I guess that's how the density is used in this scenario. Okay. This is still running here in the background doing some mesh optimization. Are there any other questions at this time? Okay. I think the key here is that when running the scenario, if we were actually to, let's actually look at maybe just this TPMS structure here itself. So if we look at this at the model of this guy, and actually I just want the mesh of this guy. So if we look at this property, so if we had, say, in this case, we have nodes, we have 64,000 nodes. So, and we have 6 degrees of freedom associated with each node. And if we were to multiply that, say, by 1 million lattices, or you could see how that would become a quite intractable problem later on in terms of analysis, because this would be a huge matrix. So in this sense, this homogenization provides a lot of opportunity to actually solve your problems, trying to fill this guy with lattices in this case, right? Or the actual TPMS of the structure. So I think the solution is still running a little bit in the background. Looks like we're waiting on some meshing. And then, okay, it looks like we answered Lynn's question, so that's great. And then can we apply this to elastic materials? Yeah, so in this scenario, right, we are treating, nTopology allows you to input both. Just create a new session here. Let's see, right here. So nTopology allows you to input orthotropic materials here in this scenario, and then you can put in all those values here. So we would derive these values from that compliance matrix. We're getting ready to actually add the full 6x6 matrix associated with anisotropy, or materials that have an anisotropy, right? And this is in addition to the traditional just elastic, isotropic elastic properties associated with part, where it would just be one value. So in this case, we're actually passing that full compliance matrix associated with anisotropy, or materials that have anisotropy. Okay. And do you have one infill unit cell? Gentleman has asked if we have a one infill unit cell. In this scenario, we are keeping a uniform unit cell for this guy. In this case, both a uniform TPMS structure and a uniform lattice structure. Hopefully that answered that question. And it looks like our solution did run in the background. And so in this scenario, we can actually look at our directional material properties now. And you can see now the directional stiffness is much higher for this part than previous, right? And this is because we've biased this in the vertical direction. One last piece I wanted to build off of. If you ever have questions about when to choose the lattice infill, I highly recommend, let's see if I can get the window here. I highly recommend referencing, hopefully I'm saying Oreb Al-Khatan's papers, specifically this one on topology, mechanical properties of 3D printed structures. And I just wanted to touch on this. This is a great paper where you could actually use nTop to help generate some of these structures. But what he's done here is, Oreb's actually gone through and actually done compression testing on these different lattice structures, and you can actually see the different types and how they compare relative to one to the other. So for nTop, with our analysis, we can just give you the stiffness, but in this case, through experimental testing, you can actually see the compressive loading that these guys are able to take. So hopefully that's great. I'll make these available, this link to Oreb and the documents later if there aren't any other questions. Oh, I do have one last question. It's can we simulate a graded lattice? Yeah, and so I won't be able to demonstrate it here, but I will show. Just pull up one example here. I guess the idea. Let's see if I can. So in terms of material properties, we can actually provide a material property as a field, right? And if you've seen in some of our other examples where we maybe grade a lattice or vary that lattice using a field, we can actually do the same thing with this block associated with a material property, where I can actually use a lattice and variable inputs to do that same. So we got another question now. It says, is the unit cell optimized based on the performance of the macro scale structure performance? Yeah, so in this scenario, I'm just providing an example of how we can use this homogenization technique to analyze the structure. So what we could actually do in this scenario is if we actually looked at this, the analysis of this guy, and say maybe we weren't happy with the displacement associated with this part, right? We could actually use the field associated with that part, and we could use that to variably thicken the lattice to make it more dense in areas maybe where we had high displacement, or in this scenario, we also have stress available as well associated with that part. Just make sure that's isolated. And so we could actually use the stress field. In this case, it's a little boring. Maybe we'll change the sizing of that. Yeah, so in this case, it's a little bit exaggerated here, but now we could actually use this stress field of the lattice from homogenization to actually variably thicken that as well. And we have some tutorials and guides on our support how to variably thicken a lattice using that field. Hopefully that answers some questions there. Okay, well, we've gone for 23 minutes. I hope this was helpful for folks and just going to show how nTopology not only makes it easier to analyze or to generate these lattice and periodic structures, but also easier to analyze them as well. Just have to take a slightly different approach versus the brute force of meshing in, trying to analyze each and every individual lattice structure, but how we can actually use this simplified technique to get closer to where we want to in a quick and easy way. So thanks again.